Welcome back. Today we are going to go into our lecture number 12, and we are already gone through 6 chapters in the subject of aircraft propulsion systems, and today we will look into the shaft engines, turboprop, turboshaft, as well as the prop fan topics. In terms of the layout of this lecture, we are going to look into the overview of shaft engines, turboprop, turboshaft, and prop fan, and we are going to try to finish the turboprop engine, and we shall continue for the subtopic of turboshaft, prop fan, and the summary in our lecture number 13 next week. So for today, we are going to just cover 7.1 and 7.2. In terms of the overview, this chapters introduces 3 types of shaft aero engines. Okay, because last 3 weeks we have already looked into the turbine engines, the turbojet and turbofan. So we are now moving into another family of gas turbine engine, which is the shaft aero engine. So we will look into turboprop, turboshaft, as well as the prop fan engines. The piston engines, together with these 3 engine types, complete the group of shaft engines. Turboprop engines have their exhaust gases leaving the engine at a very low speed, while the exhaust leaves turboshaft engines at nearly 0 speed. So there are 2 main difference between a turboprop as well as a turboshaft engine in terms of the exhaust gas speed. The power, rather thrust, is the key factor in both turboprop as well as turboshaft. The turboprop engines power many commuter as well as heavy transport aircraft, which flying at moderate subsonic speeds. And meanwhile, the turboprop engine is composed of 2 main parts, namely the gas turbine components, the core of the engine, as well as the propeller. We know that there are gearbox couples the propeller to the driving turbine. The turboshaft engines are normally employed in most helicopters, and some also being installed in tanks as well as boats, and some also installed in race cars. In a turboshaft engine, the gearbox is not connected to a propeller, okay, but to some other drive devices, namely rotors in helicopters as well as marine screws in the boats. Turboshaft engines also employed in other applications which are identified as industrial gas turbines, which are extensively employed in the petroleum industry as well as electrical power station. In terms of the prop fan, the prop fan engines normally being combined many features of both the turbofan as well as the turboprop engine. However, there are distinct from the both. Both means turbofan and turboprop. The prop fan engine uses gas turbine to drive an unshielded propeller, like a turboprop, but the propeller itself being designed with large number of short, highly twisted blades, similar to the fan of a turbofan engine. And that's why it's called a prop fan, a propeller fan. The prop fan engines have the highest propulsive efficiency among all air-breathing engines, including the shaft-based, ram-based, as well as the turbine-based engine. Okay, that's a little bit in terms of the overview. of the three type of engines that we are going to go look into our chapter number 7. So for today, we are going to go in term of the discussion for the turboprop engine. We will look into the overview, followed by the milestone, and then the thermodynamic analysis of turboprop engine. And then hopefully by end of the 7.23, we'll have a short break to continue. Right after that, we will continue equivalent engine power, fuel consumption, and analogy with turbofan engine. Okay, that's the plan for our today's lecture. Okay, so the picture shown here, basically it is a Cessna 208B SKS Caravan. It's a classic aircraft having a turboprop. Like what being said here, many bush airplanes like this Cessna Caravan, as well as the Quest Kodiak, which are low-speed transport or cargo aircraft, and small commuter aircraft normally uses turboprop propulsion. Right? In this example, it is a high wing. Right? They have installed a front propeller there, right? And having a turboprop engine. However, some large military and civil aircraft, such as the Lockheed L-188 Electra, shown here in figure 7.2, as well as the Tupolev Tu-95, uses turboprop engine as well. In this particular case, it is a low wing where there are 4 turboprop engine being installed on the wing itself. A distinguished application for turboprop engines such as the Bell Boeing V-22 Osprey, given in this figure 7.3, you can see that the orientation for the turboprop engine, they can be tilted. It is for the purpose of takeoff, for the purpose of cruising. Okay, it is as you can see here, the side view, right? During when it has the propeller being tilted, so that it can has a forward movement. Or in this particular figure, it is for vertical movement, right? And then you can see in the front view as well as on the top view. So a tilt rotor military aircraft that has both vertical takeoff and landing, VTOL and STOL capabilities. This particular Boeing V-22 Osprey being powered by the Rolls-Royce Allison T406 turboshaft engine. The turboprop uses a gas turbine core to turn a propeller. If you still remember what is the core of the gas turbine, you have the compressor, you have the combustion chamber, as well as the turbine. So those are the 3 main components of a gas turbine that is being connected to a gear to turn the propeller, where the propeller engines develop thrust by moving a large mass of air through a small change in velocity. That's how it's gain its thrust. The propellers are very efficient and can use nearly any kind of engine to turn the prop, and the propeller is driven through a reduction gear. Because why we need a reduction gear? Because of the revolution per minute, the RPM for the propeller will not be the same as the one in the compressor and the turbine. So it is we have a reduction gear by either the compressor turbine shaft or a power or free power turbine shaft. Okay, depending on the design of the turboprop engine. The reduction gearbox converts high revolution per minute RPM or low torque output to a low RPM high torque output. Okay, the turboprop power is measured in terms of the total equivalent power, TEP, either measured in horsepower or kilowatts. The major parts of this total equivalent power, TEP, is generated by the propeller, while its minor part is developed from the exhaust gases. So there are power generated mainly by the propeller, but there are also some minor part of the total equivalent power generated by the exhaust gases as well. A turboprop have higher propulsive efficiency than a turbojet. Of course, that's why most of the transport cargo aircraft uses a turboprop system instead of a turbojet and turbofan when they fly under 30,000 feet. Okay, and a speed requirement below 400 to 450 miles per hour. So this is due to the low jet velocities of both the propeller as well as the exhaust. The propeller become less efficient if you have speed higher than stated here. When the speed of the aircraft increases, especially above 450 or 500 miles per hour, it become less efficient. Right? In this case, the flow may reach or even exceed the sonic speed along the outer portion of its blades, giving rise to a substantial increase in the drag coefficient and awful decrease in the lift coefficient. That's why it is not recommended to use turboprops at a higher speed operation of an aircraft. A turboprop engine may be single or double or triple spool. All right, so it can have a different configuration. For a single spool engine, the only one turbine drive, the only one compressor, okay, because it's single spool, so you will have one compressor, set of compressor and one set of turbine that is connected through a shaft as well as the propeller. You can see here in this particular figure a schematic diagram of a typical engine, a single spool turboprop engine. So you have the centrifugal compressor as well as the axial turbine at the rear of the engine that is connected via one shaft, right? For a two-spool turboprop, which is composed of one or two compressor and two turbines, and that's where you have high pressure compressor, low pressure compressor, and high pressure turbine and low pressure turbine. The low pressure turbine drives either the single compressor or the low pressure compressor. Okay, and if two compressors are present and also drive the propeller as shown in figure 7.5, and the figure 7.5 is twin spool turboprop schematic diagram. A low pressure turbine as shown in this picture A. Okay, so it drives the propeller. Okay, you can see that there's a propeller there, reduction gear in front of here, and there is for the shaft that is connected to the low pressure turbine. A low pressure turbine connected to the gearbox as well as the the propeller. Meanwhile, for the compressor being connected to the high pressure turbine over here. And this is a two-spool type of engine. And then you have also low pressure turbine which drive both the low pressure compressor and the propeller as shown in figure B. And so this is another arrangement of this type of configuration for two spool or double spool type of turboprop engine. Okay, you can either have low pressure turbine which drive the propeller, or the low pressure turbine drive both the low pressure compressor as well as the propeller. All right. Finally, the three-spool engine. Okay, it's much more complex, much more heavier. It's shown in this figure 7.6. In this case, the propeller is driven by low pressure turbine. So the gearbox here, the propeller in front here, it is driven by the low pressure turbine. Okay, and the exhaust velocities of the turboprop is slow and contributes little thrust because most of the energy of the core hot gases has gone to turn the drive shaft. So to turn the big propeller in front of the engine. Moreover, the turboprop engine may be either of the pusher or a tractor type. Right? It can be either the propeller is in front of the engine or being installed behind of the engine. A pusher type turboprop engine are installed to either the wing or the fuselage, and two possible wing locations are seen, namely mid-wing or the wing tip, and depending on the configuration, and some of it having the engine being installed at mid-wing or at the front of the wing tip. And concerning fuselage, turboprops are either installed to the aft pylon or the aft end, okay, depending on the aircraft design itself. A tractor types of turboprop engine have three possible types of installation, and namely it can be installed at the wing, it can be installed at the fuselage as well as the tail side. Right? A turboprop are either installed to the mid or the tip of the wing, and concerning fuselage, two possible locations are seen, namely forward or aft fuselage pylon. And finally, tail installation shows three possible positions, namely low, median, or tip of the horizontal tail. So you can have many configuration depending on the needs, depending on the of course there are advantages and disadvantages for different type of configuration and location of the engine where it is being installed. Okay, let us move into the next part, 7.2.2. We will look into the milestone of a turboprop engine. The early name of a turboprop engine was basically, it is called air screw turbine engine because you have the big propeller there, which was later given the neater title of a turboprop. Okay, the Hungarian Georgi Jendrasik, which a designer of aircraft designer, the very first working turboprop engine in 1938, which is called CS1. It was produced and flown in Czechoslovakia between 1939 and 1942. So the engine was fitted to the Varga XGXH twin engine recon bomber, but proved very unreliable. Okay, because this is the early stage of the design of the engine. Since 1940s, Rolls-Royce in the UK built several turboprop engines. As example, RB50 Trent, which powered the world's first turboprop-powered aircraft, the Gloucester Meteor, which flew on September 20, 1945. They also have another type of engine called Clyde. It is in August 1945, which powered the West Lion Wyvern TF-Mk2 strike aircraft, right? And then also the Dart aircraft, that engine, which powered several aircraft, including Fairchild Industries F-27 and Grumman Gulfstream. And more than 7,100 Darts engine were sold worldwide, flying over 130 million hours. So it's quite popular during those days in 1940s, 1950s. At the same time, Rolls-Royce also built engine called Tyne type of engine in April 1955, which is a two-spool engine driving through a double pi cyclic gearbox and four-blade reverse propeller. They also have Merlin engine 1965-1998, powered Swearingen SA226T and AE2100, which powered the Saab 2000 fighter aircraft. Okay. Another British manufacturer was the Bristol, which built Theseus that powered the Avro Lincoln aircraft, 1945. Proteus that flew millions of hours and still drive the biggest hovercraft aircraft across the British Channel, 1947. And a third British manufacturer, Armstrong Siddeley, which built Phaeton that powered the Westland Wyvern Carrier Strike Fighter in 1945, and they also produced Mamba, which powered Douglas C-47B Dakota, and Double Mamba, which powered the Ferry Garnet in 1946. So move on to the American turboprop manufacturer, GE, General Electric. They have a T31 type of engine, which is the first American turboprop engine that powered consolidated Vultee XP81 and first flew on December 21st, 1945. This type of engine was mounted in the nose with the J33 turbojet, which is mounted in the rear fuselage to provide additional thrust. So similar turboprop or turbojet combinations were also used in the Navy XF2R1 type of aircraft. Another excellent engine by General Electric is T56. We have seen T56 family in the turbojet lecture last few weeks, and this T56 turboprop powering the Lockheed Martin C-130H. Okay, this is the C-130 type of transport aircraft, and C-2A Greyhound, right? And T-64, another type of engine powering de Havilland Canada DHC-5, as well as the Buffalo aircraft. Another US aero engine manufacturer is Allison, which produce several turboprop engine. We have GMA 2100, T56A11, and T406 turboshaft engine that powers Bell Boeing V-22 Osprey aircraft. Okay, you have seen this, the type of the aircraft just now, which has a the engine can be tilted either forward or for short takeoff and landing and vertical takeoff and landing. A third US manufacturer for turboprop engine is Allied Signal, okay, previously known as Garrett AI Research, that produced the famous TPF331 turboprop engine, which powered, for example, the Embraer FAMA CBA123, which is one of the few pusher turboprop in recent days. So basically, the propeller seated at behind of the engine. It is a pusher type of aircraft. In the Soviet Union, we have the Kuznetsov Design Bureau, okay, which produced in 1950s the NK-12 turboprop engine that powered Tu-95 strategic bomber. Okay, and they also with the propellers that had supersonic tip speeds. Okay, another Russian turboprop manufacturer is the Kirill Klimov Experimental Design Bureau. An example for its engine is Klimov TV7-117 that powers Illusion 2, 112 and Illusion 2-114, right? So I purposely leave all the pictures for the engine for you to explore, and you can just Google and try to find the respective engine pictures, so that you can have your own self-learning. Moving into the Ukrainian company called Motosich, which is one of the largest engine manufacturers for airplane and helicopters worldwide. It produced AI-20D series type of engine and AI-24 series of engine. Okay. Canadian famous company Pratt & Whitney of Canada, normally known as PwC, built a big family of the popular turboprop or turboshaft engine, including the PT6, PT6A, and so on. There's so many series of the family, as well as PW100 and PW200. Looking into the PT6A, which comes in 65 different versions, you can see that, it is a quite popular engine. It is evolving and having many different versions, with engine power ranging from 500 shaft horsepower to 2000 shaft horsepower SHP. Okay, so since the PT6A family entered service in the 1960s, there are around 40,000 engines which have been produced. Okay, to date, PT6A has accumulated around 300 million flying hours or more, and it is therefore a highly proven and durable engine. So it powers numerous aircraft, including Beechcraft 1900, the Dornier, Bell, and Sikorsky type of aircraft. In France, there is another company called Turbomeca, which began producing small turboprop engine in 1947. They have a type of Markadau engine, first turboprop built in 1953, generating 400 horsepower. The Bastan in 1957, and Astazu in 1957, which developing 523 to 644 horsepower, which is the most famous French turboprop that powered many aircraft, including Mitsubishi Mu-2 and Dornier DO-27 Ti. Other worldwide companies, including Italian Fiat, that built turboprop T64 P4D, right? And there are also Japanese company IHI. There are also another company called EPI Europrop International. This is a German company, okay, which created the 4 leading European aero engine companies: Industria di Turbopropulsores, MTU Aero Engine, Rolls-Royce, and Snecma. They form a consortium that produces 3-shaft TP400 D6 turboprop, which currently powers the Airbus A400M military transport. Right, let us move quickly into the thermodynamic analysis of turboprop engine before we have a short break later on. For the thermodynamic analysis, we will look into single spool turboprop and 2-spool turboprop. The different modules of a turboprop engine are the intake or inlet, 1 or 2 compressor, a combustion chamber, and 1 or more, maybe up to 3 turbine, and then the exhaust nozzle. So we will look into the thermodynamic analysis of different section. With regard to single spool turboprop, a simplified layout of a single spool turboprop engine together with its temperature entropy diagram, TS diagram, is shown in the following figures 7.7 and 7.8. So the flight speed is expressed as U equal to the Mach number to the square root of specific heat ratio, gamma, the R, the gas constant R, as well as the temperature of the ambient. The different module of the engine are treated hereafter. Right, so figure 7.7, layout of single spool direct drive turboprop engine. So take note on the section here, section A in front of the propeller, and then section 1 right after the propeller. Section 2 basically inlet of the compressor. Section 3 is the outlet of the compressor going into the combustion chamber, and section 4 is the section after the combustion chamber going into the turbine. Section 5 right after the turbine, and section 6 is the exit of the nozzle. And this is the TS diagram looks like. It is a typical turbojet or turbo jet engine TS diagram. Okay, nothing fancy there, because you see it is a single spool turboprop engine. Okay, we look into the intake, where the intake has an isentropic efficiency zeta D. Okay, we call zeta D normally is for the diffuser, and the ambient temperature as well as the pressure, PA and TA respectively. The flight Mach number is given as MA. The temperature and pressure at the intake outlet, right, after the at the station 2, it is a TO2 and PO2, which may be calculated using the same governing equation that we have already described in our earlier chapters. Then we move into the compressor section. For a known of compressor pressure ratio pi C and its isentropic efficiency zeta C, the outlet temperature and pressure are calculated using the previous method, and the specific power for the compressor is given by the following relation. Okay, 7.1. Moving into combustion chamber, with known combustor efficiency zeta B and pressure drop in combustor, the delta P, then the pressure at the outlet of the combustion chamber, and the fuel to air ratio F are calculated in the same way as we have already discussed in the turbojet engine chapter. Moving into the turbine, since the turbine drive the compressor as well as the propeller, and the portion of the power transferred to each is not known in advance, then it is not easy here to determine the outlet pressure and temperature of the turbine. However, let us first examine the power transmission from the turbine to the propeller as illustrated in figure 7.9. So over here, we can see a figure of expansion in the turbine. We have and the nozzle of a single spool turboprop, right? So this is 6 is if you remind back, you can, it is the ambient exit of the nozzle. 5 is the station where right after the turbine, and 4 is the station before the turbine. Okay, this is the enthalpy to entropy diagram, H against the S at different location, section A, and then section PO5 and PO4 over there, right? Moving into the turbine, only a portion of the turbine power is delivered to the propeller. Okay, this propeller power is dependent on several efficiencies. We have the mechanical efficiencies of the turbine, zeta MT, the mechanical compressor efficiency of the compressor, zeta MC, as well as the propeller itself, zeta G, okay, sorry, zeta PR, the propeller efficiency, okay. And figure 7.9 illustrate the enthalpy entropy diagram for the expansion processes through both the turbine and the exhaust nozzle. There is an optimum exhaust velocity that yields the maximum thrust for a flight speed the turbine inlet temperature and given efficiencies. Now define the following symbols as shown in the figure 7.9. We have the delta H enthalpy drop available in an ideal isentropic turbine and exhaust nozzle. The alpha delta H, which is equivalent to the delta HTS, which is the fraction of the enthalpy drop that would be available from an isentropic turbine having the actual pressure ratio. And then finally the delta H and S, okay, which is actually the fraction of the enthalpy drop that may be available from the isentropic nozzle. To continue, the zeta T is basically the isentropic efficiency of the turbine, and zeta N is the isentropic efficiency for the exhaust nozzle. T is for the turbine, small n here is for the nozzle, and these parameters will be evaluated in terms of the following thermodynamic relations. Okay, you have this relationship, equation 7.2, which resulted to get the enthalpy drop and the change in enthalpy. So it was assumed in the above equation, equation 7.2, that the ratios between specific heats, okay, gamma T, which is equal to gamma N and gamma H within the turbine and the nozzle, right? So the exhaust gas speed UE, the speed that leave the nozzle section, is given by the relation, and the following relation can be used to find the exit exhaust velocity 7.3. The procedure to be followed here is basically to deduce a mathematical expression for the thrust generated by the propeller, TPR, from the power generated by the propeller. Adding this thrust to the thrust generated by the exhaust gases, then the total thrust is obtained as a function of the alpha. And differentiate this total thrust with respect to alpha, we can now obtain the optimum value of alpha, giving the maximum thrust. If you can see here, the propeller thrust TPR can be correlated to the propeller power, okay, by the relation. We can see that there is a W shaft over there, where shaft power is basically in terms of the mechanical turbine efficiency, and we can also have the mechanical compressor efficiency in this expression, right? The turbine specific power is also given here, delta HT, okay, which is equal to the efficiency of the turbine times alpha times the enthalpy change. The mass flow rate of the air, m dot A, is the air induction rate per second, and the amount of air being sucked into the core of the engine, and the fuel to air ratio and the bleed ratio are defined over here. The thrust force obtained from the exhaust gases leaving the nozzle is denoted as Tn, okay, and can be expressed by this relation. You can see that there is a UE minus U there. U is the exhaust speed, and U is basically the aircraft speed. Oops, okay. The total thrust for the turboprop single spool engine equal to the thrust produced by the propeller and thrust produced by the nozzle, and it can be expressed in this equation 7.5. We can now differentiate equation 7.5 with respect to alpha. We get the optimum value of alpha OPT, alpha optimum, that maximize the thrust for fixed component efficiencies, flight speed, compressor specific power, and the expansion power delta H, and this optimum value is expressed in this equation, and all the efficiency being grouped over here, okay, and that is resulted to equation 7.6. So this particular value of alpha define what we know as the optimum power split between the propeller and the jet. Substituting the value of alpha optimum power in equation 7.5, which gives the maximum value of the thrust force. And the corresponding value of the exhaust speed is given by the following equation. Right? This is where the relationship between the exhaust speed and the aircraft speed and the respective efficiencies. Okay, I think we can still go for a couple of more minutes to finish up turboprop engine, two-spool turboprop, thermodynamic analysis of turboprop engine. And over here, we have the schematic diagram of a two-spool engine having a free power turbine together with its temperature entropy diagram, which is shown in figure 710 and 711. The low pressure spool is composed for the propeller and the free power turbine, while the high pressure spool is composed of the compressor and high pressure gas generator turbine. So this is the case for the two-spool turboprop, right? So as the layout is given here, right? So you can see the shaded black area over here is connected to the propeller, and this is the turbine. This is the low pressure, high pressure turbine connected to the compressor. And 711 figure temperature entropy diagram for a free power turbine, and we'll go through the two-spool turboprop analysis over here. The different components are examined here. And first is the gas generator turbine, and energy balance between the compressor and this high pressure turbine gives expression 7.8a, right? And the specific work generated in the turbine of the gas generator is given by 7.8b, right? Moving into the equation 7.8 with known turbine inlet temperature TIT, this is given by T04 over there. Then the outlet temperature T05 can be calculated, right? Moreover, the isentropic efficiency of the gas generator turbine, the outlet pressure P05 can be calculated using this expression. For the free power turbine, the work developed by the free power turbine per unit mass inducted into the engine, okay, you can see there HFT, okay, is a free turbine, as noticed from the above equation, previously explained in earlier section 7.2.3.1. For the single spool turboprop, the temperature T06 is unknown and cannot be calculated. All right. So similar procedure will be followed, referring to figure 712, which defines the successive expansion processes in the free power turbine and the nozzle. We have delta H, the enthalpy drop available in the ideal or isentropic turbine, and exhaust nozzle, assuming full expansion. We assume it is a full expansion to the ambient pressure, where the P7 will be equal to the PA. This is ideal, but it's not true in the real situation. You can then get the enthalpy drop for this situation for two-spool turboprop pre-power turbine. Looking into the alpha delta H, which is equal to the delta H free turbine FTS, which is the fraction of the enthalpy drop that would be available from an isentropic free power turbine having the actual pressure ratio. Okay, So zeta ft is the isentropic efficiency of the free power turbine. And following the same procedure described earlier to determine the optimum alpha, the propeller thrust and the exhaust thrust are determined from this relation. Okay. The total thrust now can be found where we have T equal to TPR plus Tn. Okay. And using expression of equation 710, you can now find the total, the specific thrust, T over m dot, okay, where zeta mft basically mechanical free turbine efficiency. Maximizing the thrust for fixed component efficiencies, the flight speed U and delta H yields the following optimum value. You can get the alpha OPT using 7.11. Again, it can be mentioned that this particular value of alpha define the optimum power split between the propeller and the jet. Substituting the alpha OPT, okay, the optimum in equation 710, which gives the maximum value of the thrust force. And the corresponding value of the exhaust speed is given by equation 712 over here, okay. And in terms of the outlet conditions at the free turbine are easily calculated from the known delta H and alpha optimum. As an alternative to the parameters alpha discussed above, two methods may be followed where we can have a known exhaust speed and then a known the ratio between total static pressure at the nozzle outlet X. Okay, I believe that would be nice for us to have a break before we continue the remaining of the topic on the turboprop engine. Okay, we have a break for 10 to 15 minutes and we shall continue afterwards. Thank you very much. Okay, I believe it is already there, right? So we have started to look into the turboprop engine. We start with the overview of a turboprop engine and then going through the historical background, the milestone of a turboprop engine, how it's all started until the current or the recent usage of turboprop engine in modern transport, especially the military type of aircraft. And before the break, we look into the thermodynamic analysis of a turboprop engine. Okay, and now we shall continue the remaining subtopic. We will first look at the equivalent engine power. With regards to the equivalent engine power, there are two conditions. One is at the static condition and the other one during flight operation. So we will look into what are the corresponding equations involved to find the equivalent engine power. The two flight phases will be discussed, static run and the cruise conditions. The first one is static condition. During testing on the test bench, okay, normally the type of engine or turboprop engine will be tested in the laboratory or at the test facilities to ensure that what are the whether the engine can operate by design or it is need to be further modified. So during the testing or takeoff condition, the total equivalent horsepower, we call it as the TEHP, total equivalent horsepower, and the is equal to the SHP, the propeller plus the SHP equivalent to the net thrust. For estimation purposes, it is taken that under sea level static conditions, one shaft horsepower, okay, the is equivalent to approximately 2.6 pound of the jet thrust. So we have expression 713A here. The total equivalent horsepower during takeoff is equal to the shaft horsepower plus the jet thrust as 2 points jet thrust over 2.6. One SHP is equivalent to approximately 2.6 pound of the jet thrust. If you would like to go into the SI unit, experiments have shown also that the total equivalent power, TEP in kilowatt, is related to the shaft power, SP. Just now we look at the shaft horsepower, SHP, which is also being given in kilowatt by this relation, where we have expression 713B, the total equivalent power TEP in kilowatt at the takeoff condition is equal to the shaft power in kilowatt plus jet thrust in Newton over 8.5. Okay. Because 8.5 is equivalent to 2.6 pound, which is equivalent to 1 shaft horsepower. The thrust on the test bench or the ground testing or in the during takeoff is given by this expression, right? So you have the thrust produced equal to the mass flow rate of air coming into the engine times 1 plus the fuel to air ratio F minus B times the UE, the speed of the exhaust velocity. Now let us move into the another condition, the flight operation. For a turboprop, during flight, the equivalent shaft horsepower ESHP is equal to the shaft horsepower plus the jet thrust power as the following relation. So ESHP, equivalent shaft horsepower, equal to the SHP shaft horsepower plus the thrust times the velocity of the aircraft speed divided by a constant time the efficiency of the propeller, right? We know that the thrust itself equal to the mass flow rate times this expression, which we have already seen in our previous slide. Okay, so you can then get the equivalent shaft horsepower using expression 714A, right? The constant for in equation 619A, okay, depends on the employed units. Thus, the depending on the unit that you are using, whether it is velocity in feet per second, thrust in pound, or you are using miles per hour, all right, or you are using knots and inches a feet per second, so you can using different constant, right? So depending on the type of units, okay, 714B, right? So this constant equation is actually not equation 619A, is actually equation 714A, right? There's a mistake over here. Normally, a value of the propeller efficiency, zeta PR, is roughly around 80%. We can, which is employed as the industrial standard. So very rare we have a very high propeller efficiencies, 99% or 95%. So normally they will take it as 80% propeller efficiency. Right. Let us move into 7.2.5, how we are going to calculate the fuel consumption for a turboprop engine. As previously explained, during the past 3 weeks, we look already for turbojet and turbofan engine. The fuel consumption is defined as the thrust specific fuel consumption, TSFC, which is defined as TSFC equal to the m.f, mass flow rate of the fuel, over the thrust. Okay, the thrust specific fuel consumption equal to the mass flow rate of the fuel over the thrust itself, and expressed in terms of kilogram fuel per Newton hour. All right, that is what we have already seen in our previous chapter number 6. For a turboprop engine, the fuel consumption can be identified by what we say as equivalent specific fuel consumption, right? ESFC, right? Okay, and then it is actually being defined as equal to the mass flow rate of the fuel over the equivalent shaft horsepower, ESHP, and being expressed in the following unit. You can have it in kilogram fuel per kilowatt hour. Typical values for equivalent specific fuel consumption are around 0.26 to 0.36 kilogram fuel per kilowatt hour, depending on the type of the turboprop engine. Let us go through one example. Okay, since we have time today, we can go into example 7.1. A two-spool turboprop engine. Okay, once we put a two-spool, you have to put in your mind that there are either two set of compressor or two set of turbine, and the low pressure turbine is connected to either the low pressure compressor and the propeller, or the other type of the other high pressure turbine is connected to the high pressure compressor. And this is just one of the possibility. All right. So the two-spool turboprop engine with the propeller driven by a free power turbine is considered. In this particular case, it is required to calculate the equivalent shaft horsepower, ESHP, and the equivalent specific fuel consumption, ESFC, in the following cases. One is the static condition. Given that the mass flow rate for the fuel is 1,500 pound per hour, the thrust is 600 pound fuel, and the shaft horsepower is given by 2,800 value. And the second condition is the flight condition, where we have the velocity for the aircraft is 330 feet per second. The mass flow rate for the fuel is 1,000 pound per hour, and the thrust produced is 300 pound fuel, and the the shaft horsepower is 2,000. The propeller efficiency is given as 0.8. So this is another condition. So you have the static condition and the flight condition. Don't mix it. You have to solve one by one. For the static or ground run condition, the ESHP, equivalent shaft horsepower, and the equivalent specific fuel consumption can be calculated using the following relations, right? So you have ESHP equal to SHP plus T over 2.5, which is equal to, and you have given SHP 2,800. You are already given the thrust at 600 pound, which is divided by 2.5, which is equal to 3040 horsepower. Right? For the equivalent specific fuel consumption, the M dot F is 1,500 given already. ESHP, right? You put the value that you already calculated for ESHP into this expression. You can now get the equivalent specific fuel consumption to be 0.4934 pound per ESHP hour. Right? So you already done for the part A for the static condition. For the flight condition, when you want to find ESHP, you have to use the expression, right? Since it is given in the flight speed is given in what is it called? Okay, feet per second. So you have to use 550 as the constant, right? So don't get it wrong or mix. You use a different constant for miles per hour, for knots, and other type of units, right? So this is a common mistake. Okay, you use the wrong equation for different units. Okay, so you can then put in terms of the numbers given. We have already given the shaft horsepower. You already know the thrust. You have the velocity. You have the propeller efficiency. Then you get the equivalent shaft horsepower to become 2,250 horsepower. And then we continue to find the equivalent equivalent specific fuel consumption. I'm very sorry. ESFC. So you have the mass flow rate of the fuel, which is 1,000, and you already got the value of ESHP, which is 2,250 horsepower. You obtain the equivalent specific fuel consumption to be 0.4494 pound fuel per horsepower hour. All right. So this is during the flight. Okay. You can see here, it is not that different. For static condition, it is 0.4934. For during flight, it is 0.449 for equivalent specific fuel consumption. Because you consume more fuel for takeoff or at static condition compared during cruising at flight. Let us go into another example. We have example 7.2. A double spool turboprop engine is installed to an aircraft flying at a speed of 200 meters per second. We have an altitude of 6 kilometers. The condition of the ambient temperature is 249 and the ambient pressure is 0.472 bar. Okay, the maximum temperature, turbine inlet temperature is set 1,400 degrees Kelvin, and the fuel heating value Q HV equal to 43,600 kilojoule per kilogram. It has the following particulars. So there are many information given here. Okay, mass flow rate is given 14.6 kilogram per second. The compressor ratio, low pressure compressor 8.5, high pressure compressor pressure ratio 2.35. The pressure for the combustion pressure change in the combustion chamber 2%. Okay, the inlet or diffuser efficiency already given, and the remaining. So you have to take note all of this in order for you to use later on. Even the bleed percentage B is given, alpha also given, specific capacity at constant pressure for the compressor, and then for the turbine and the nozzle also given. Okay, what you need to find, basically it is required to calculate the following. One is that you have to find the equivalent brake horsepower, EBHP. And then you have to find the ratio between the thrust forces generated by the propeller and the nozzle. And finally, finding the optimum alpha. So in terms of the solution, this two-spool turboprop is composed of the following modules. So you have the intake, which is state 1 and 2, low pressure compressor state 2 and 3, coupled from both sides to the low pressure turbine and propeller, high pressure compressor states 3 and 4, combustor state 4 and 5, high pressure turbine state 5, 6, which drive the high pressure compressor, and low pressure turbine state 6, 7, and nozzle is on stage 7, 8. Okay, successive analysis of the elements will be given below. For the intake, if you look at the sonic speed, you want to find what is A, right? So you use the expression to find the speed over there. You get 316.3 meter per second. You can find the Mach number given you already. You have already obtained, already given over A. A is already what you already find here. You can get the Mach number is 0.6323, right? The moment you get Mach number more than 1, meaning that you are putting the wrong values. Okay, so just have a check and common sense saying that turboprop flying less than Mach 1, okay, at the sonic speed. And then you can find the TO2 using the expression for TO2. You get 268.9 Kelvin. You can also find the PO2 for the intake, which is we know that it is equal to 1.0736 PA, right? You already have PA value at 6,000 kilometer. You can now get the PO2, which is equivalent to 0.5067 bar. Moving into the low pressure compressor, state 2 to 3. So you have P03, put the low pressure compressor value, right? And then you get P03 at 4.307 bar. And the temperature at 03 at the compressor state end of this compressor is 542.4 Kelvin, right? The specific enthalpy rise can also be found as 274.87 kilojoule per kilogram. Moving into the high pressure compressor, okay, P04 is 10.12 bar and T04 is 719 Kelvin, right? So this is before it goes to the combustion chamber. In the combustion chamber, right, the pressure, you already been given the pressure drop or PCC value, which is 2%, and you get the pressure at state 4.5 or PO5 9.19 bar, and you can also find the the fuel to air ratio to become 0.0197, considering the air bleed, already given air bleed, which is 0.0821. Okay, you put all the values there, you can get the fuel to air ratio value F. Going into the state 5-6, high pressure turbine, energy balance between the compressor and the turbine. You put all the expression, putting the numbers, you will get T06 value 1234.7 Kelvin and P06 value 5.726 bar. Okay, combine the low pressure turbine and the nozzle state 6 and 8. Right, you will get T8 S equal to 661.6 Kelvin and the enthalpy drop equal to 657.938 kilojoule per kilogram. And low pressure turbine specific power, right? So you can put the expression over there. You already given alpha and the remaining of the values that you already obtained. Okay, and you can then get T07, which is equal to 718.9 Kelvin, and P pressure at station 7 is 0.68658 bar. The shaft power, which is equivalent to this expression, and the propeller specific power PPR is given by the relation over here, and that leads us to the propeller specific power, which is over the mass flow rate. You get 173.625 kilojoule per kilogram, and that is the answer for the propeller specific power PPR, PPR over M dot A. The propeller thrust is correlated to the propeller power by the relation. So you can get, so you already got the value for the propeller power, specific power. You know the velocity of the aircraft, then you can get the propeller thrust, specific propeller thrust to become 868.12 Newton kilogram. Okay, moving into the nozzle part, the last part, the exhaust gas speed UE can be obtained by the following relation. So you get a UE equal to 353.6 meter per second. The thrust force obtained from the exhaust gas leaving the nozzle is denoted as Tn, given by the relation here. So specific thrust at the nozzle, Tn over m dot equal to 131.5 Newton per kilogram. Hence, the total thrust, you already got TPR. Now you have Tn. You can have the total thrust value of 14.585 kilonewton. Total equivalent power, okay, P equal to T thrust times the velocity. You can get 3,911.76 horsepower, and the ratio between the propeller and the nozzle thrust is 6.6 value. Optimum alpha, so you just use the equation to find optimum alpha, and you will eventually get this value of 0.9606. All right, before we end, probably best to go into the last subtopic for turboprop engine, analogy of the turboprop engine with turbofan. Okay, a turboprop engine are analogous to high bypass turbofan engine, and the propeller itself is an unducted fan with a bypass ratio equal to or greater than 25. The airflow through the propeller is slightly accelerated and thus acquire speed slightly higher than the aircraft flight speed, and the momentum difference between the inlet and outlet flow through the propeller produces the propeller thrust. Okay, next, this accelerated air passes through the engine core and accelerated to a higher speed. The momentum difference between the outlet and inlet core flow results in the core of the thrust. The thrust force is given by this relation. You have this expression 716A, okay, where you have the component of the velocity between U1 and U0, okay, and then you have the component of the fuel air ratio and the bleed air, and between the exit velocity and the U1 velocity. Introducing the bypass ratio into equation, okay, again this is a slightly wrong, not 617A, it is 716A, okay. So this is again is wrong, and you get the expression of 716B, putting the bypass ratio value over there, the specific thrust related to the engine core mass flow rate to get to this expression 716C, where for this one is just a thrust, and this is the specific thrust where you divide the thrust with the mass flow rate. Okay, so with that, it leaves us to the remaining subtopic for chapter 7, turboshaft and prop fan, and finally the summary. We shall continue the remaining subtopic next Monday in our lecture number 13. Okay, so my suggestion is that try to go through the two examples, 7.1 and 7.2, so that you can get familiar with the thermodynamic analysis for the turboprop engine. So let me just end my presentation, and we shall meet again next Monday. Okay, thank you very much, and bye-bye.